zeros using the rational zero theorem. That's what we did in 2.6. So now we're going to classify the zeros of the polynomial functions. Are they rational? Are they real? Are they irrational? Etc., etc. So we need to know the fundamental theorem of algebra. So the theorem states, if a function is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. So basically, if you have a polynomial function, that means you will have a solution somewhere, whether it is imaginary or real, you'll have a solution. So that's what complex numbers means, all the numbers, all the possibilities. The corollary, or the opposite, means if a polynomial function of degree n, where n is greater than 0, if the function is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has exactly n solutions, provided each solution repeated twice is counted as 2 solutions, and each solution repeated 3 times is counted as 3 solutions, and so on and so on. So whatever your exponent is of your function, that's how many solutions you will have for that function, even if they are repeats. All right, so let's take a look at our first example. How many solutions does the equation x to the third power plus 5x squared plus 4x plus 20 equals 0 have? So the answer is, because that function is a polynomial equation of degree 3, then it has 3 solutions. And if you were to go through the process of solving for that, you would see that those solutions are -5 and positive and negative 2i. Eventually, we're going to get to solving for those solutions, as we've done in the past, but this at least tells you, you know for sure you have 3 solutions, and 2 of them are imaginary. Part B, how many zeros does the function f of x equals x to the fourth minus 8x to the third plus 18x squared minus 27? And again, the solution tells you that it has 4 zeros because the degree is 4. And then if you were to solve it out, you would have that the zeros are -1 and then 3, 3, and 3, meaning the 3 is repeated 3 times. Now, when we list our zeros, you normally don't list all 3 3s. You would just list the 3 once, because it's only going to hit the graph 1 time at 3. But it tells you at least that's where 3 of the 4 solutions are coming from. All right, let's find the zeros of a polynomial function. So this time we have this function and we're going to find all of the zeros. So the function x to the fifth minus 4x to the fourth plus 4x to the third plus 10x squared minus 13x minus 14. So step 1, we're going to find the rational zeros of the function. And because f is a polynomial function of degree 5, that means it has 5 zeros. Go through the process that we did in 2.6, find the possible rational zeros by looking at the factors of the leading coefficient and the constant. So 14 can be factored into 1, 2, 7, and 14. And then we use positive and negative. Using synthetic division, we determine that -1 is a 0 repeated twice, and that 2 is also a 0. So then we write f of x in factored form, dividing f of x by its known factors, x plus 1, x plus 1, and x minus 2, gives us a quotient of x squared minus 4x plus 7. So we eventually get down to this quadratic equation. And then we would, so here's it all listed out. Step 3 is we would find the complex zeros. So using the quadratic formula, we would factor that trinomial into its linear factors. So negative b plus or minus the square root of b squared minus 4ac all over 2a gives us the other two factors. And when we do that process, we realize that, of course, they're imaginary. So our answer would be 2 plus or minus I times the square root of 3. And so that's why you see it written here as in factored form, because you always subtract your intercepts. All right, so our zeros are -1, -1, 2, and then 2 plus or minus I times the square root of 3. I don't expect you to write them out as 2 plus I squared root of 3 and 2 minus I squared root of 3. If you use the plus or minus sign between the 2 and the I, that's fine. But it's nice to see, hey, there are 5 zeros. All right, so the next part is we're going to talk about a couple of other theorems. So the complex conjugates theorem says if f is a polynomial function with real coefficients and a plus bi is an imaginary zero of f, then a minus bi is also a zero of f. So notice in our previous example, we had 2 plus I squared root of 3 and 2 minus square root of 3. So you had the conjugates. Irrational conjugates theorem, suppose f is a polynomial function with rational coefficients, meaning these are going to be either whole numbers or fractions or decimals that terminate. And a and b are rational numbers, such as square root of b is irrational. Then a plus the square root of b is a zero of f, and a minus the square root of b is also a zero of f. All right, so let's take a look at this in practice. Example 3, using zeros to write a polynomial function. So we are going to write a polynomial function of function f of least degree, so the smallest degree possible, that has rational coefficients, a leading coefficient of 1, and 3 and 2 plus square root of 5 as zeros. All right, so how do we do this? Because the coefficients are rational and 2 plus 5 is a square root of 5 is a 0, 2 minus the square root of 5 must also be a 0 by the irrational conjugates theorem. Because from quadratic formula, we would get 2 plus or minus square root of 5. So use the 3 zeros and the factor theorem to write f of x as a product of 3 factors. So the least degree, of course, is going to be the third degree. Okay, so write the function in factored form. So we listed out all the possible factors, x minus 3, x minus 2 plus square root of 5, and x minus 2 minus the square root of 5. Then we are going to regroup the terms. So we have x minus 2 times, and notice this time we put the parentheses around x minus 2 minus square root of 5 and x minus 2 plus square root of 5. So we're going to get that square root of 5 back. Multiply it out using our products. Now, when we do this for x minus 2 minus square root of 5 and x minus 2 plus the square root of 5, if we use a difference of 2 squares, we know that we're going to get x minus 2 squared minus the square root of 5 squared. So this has been simplified, that step has been taken out, and that's where the answer comes from. And then expand the binomial, factor it out. So x minus 2 squared is x squared minus 4x plus 4 minus 5. So simplify it one step further, and then multiply x minus 3 to all of that. And then simplify again by combining your like terms, and we get x to the third minus 7x squared plus 11x plus 3. All right, so let's check our answer. And we can check this by seeing if the zeros are true. So plug in 3. That was one of our possible zeros. And we get yes, it's equal to 0. And then you can plug in 2 plus the square root of 5. Factor it all out, and yes, it does equal 0. This is showing you the long way of how it gets to 0. And so since the two given zeros were equal to 0, we checked it out for sure. And then we know from the irrational conjugates theorem that the other conjugate, 2 minus the square root of 5, is also equal to 0. All right, so then the third main idea from this section is the Descartes rule of signs. So the French mathematician René Descartes, who was born in the late 16th century, and then most of his math was from the 17th century, of course. And so he found the following relationship between the coefficients of a polynomial function and the number of positive and negative zeros for the function. So the Descartes rule of signs says let f of x equal that long function, and let it be a polynomial function with real coefficients. So real numbers, not just rational, but real numbers. The number of positive real zeros of f is equal to the number of changes in the sign of the coefficients of f of x or is less than this by an even number. And then the number of negative real zeros of f is equal to the number of changes in the sign of the coefficients of f of negative x, or is less than this by an even number as well. So let's take a look at an example. And it does help to do this a few times, and it eventually catches on pretty quickly. All right, so the first one says determining the possible number of positive real numbers, negative real zeros, and then imaginary zeros. So here's our function, x to the 6th minus 2x to the 5th plus 3x to the 4th minus 10x to the 3rd minus 6x squared minus 8x minus 8. All right, so the first solution is we're going to substitute in x, so positive x, and take a look at the sign changes. So from x squared to negative 2x, that's a sign change. Negative 2x to 3x, sign change because you're going negative to positive. Sign change. No more sign changes, everything else remains negative. So the coefficients in f of x have 3 sign changes. So f is going to have, the function is going to have either 3 or 1 positive real zeros. Then plug in negative x. What's going to happen when you have negative x? All right, so negative x squared minus 2 times negative x plus 3 negative x to the 4th minus negative x to the 3rd plus 6 times negative x squared minus 8 times negative x minus 8. All right, when we plug this in, we have to rewrite it to account for the fact that if I have a negative coefficient, what is that going to do to my exponent? So a negative number to an even exponent is going to stay positive. So x to the 6th, 3x to the 4th, and negative 6x squared. Those did not change. But the odd exponents, 5, 3, 1, that is going to change because if you have a negative coefficient, that means your answer will be negative. And then the negative times the negative will equal a positive. So notice now, negative 2x to the 5th is now positive 2x to the 5th. And negative 10x to the 3rd is now positive 10x to the 3rd. And negative 8x is now positive 8x. Then go through and take a look at the sign changes. So positive, 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 negative, positive, negative. So we have 3 sign changes there at the end, going positive to negative, positive to negative. So the coefficients in the function of negative x have 3 sign changes, so f has either 3 or 1 negative real zeros. So the possible numbers of zeros for f are summarized in this table. And when you answer a question like this, you're going to make a table. We know from our degree that there are 6 zeros. So as we're adding up the positive real zeros plus the negative real zeros plus the imaginary zeros, it should equal 6. If I have 3 positive real zeros and 3 negative real zeros, then I would not have any imaginary zeros. If I have 3 positive real zeros and only 1 negative real zero, then that leaves room for 2 imaginary zeros. 1 positive real zero and 3 negative real zeros leaves room for 2 imaginary zeros. And lastly, if I only have 1 positive real and 1 negative real, that means I have 4 imaginary zeros. So this is just setting up the table of possibilities. All right, let's move on to example 5, approximating our zeros. As some of you have learned by using your calculator, you can solve for the zeros. You can solve for the roots using the calculator. So plug in the function x to the 6th minus 2x to the 5th plus 3x to the 4th minus 10x to the 3rd minus 6x squared minus 8x minus 8. Same function in the last example. All right, when we plug it into the calculator, we see this funny looking graph. And I can see that I had 2 real solutions, 1 negative and 1 positive, which was the final possibility in my answers on the Descartes rule of signs. And I can approximate using the solver function that the negative 0 was negative 0.732, so on and so forth, and the positive was 2.732, so on and so forth. So from these screens, we can see that the zeros are approximately those 2 values. Anytime we're rounding, again, don't use an equal sign, use the approximation sign. Squiggly equals. All right, pretty easy with the calculator. So now we are going to approximate real zeros of a polynomial model. So we're going to use a word problem here. A tachometer measures the speed in revolutions per minute, or RPMs, at which an engine shaft rotates. So this is getting into car mechanics. For a certain, or automotive mechanics, boat mechanics, same thing. For a certain boat, the speed x of the engine shaft in hundreds of RPMs and the speed s of the boat in miles per hour are modeled by this function. What is the tachometer reading when the boat travels 15 miles per hour? All right, so let's take a look at how to solve this. We're going to substitute in 15 for s of x in the given function, so that we can then rewrite by moving 15 over to the right. Rewrite the function 0 equals all of those numbers. And then plugging it into the calculator, we can approximate the value that x is equal to 19.86 when y is equal to 0. So by solving for the real zeros, we are able to determine that this is our solution. So from the graph, there's only one real zero at approximately 19.9. So the tachometer reading is about, because this was in hundreds of RPMs, so 1,990 RPMs, revolutions per minute. All right, a lot of information in that video. Chances are you're going to need to go back and review it a couple of times, and we will cover this in class next time.